Hello guys, welcome again to the new tutorial. Today we will talk about the PWM signal or pulse width modulation. As we know, most of the time we might need an analog output from our system to control devices like DC-DC converter or even dimming an LED. But most of the Arduinos available in the market like the Uno or even the high-end like the Mega, they have no DAC modules, which they are the digital to analog converter, which means they have no capability to output a variable analog output. Therefore, we will make use of the available pulse width modulation pins in the board to convert them, filter them, and buffer them, which then at the end generate the variable analog output. Okay, so you can see here these Arduino boards, they have the capability of generating PWM signals. So in this tutorial we will learn which pins of the Arduinos they support the PWMs, and also we will talk about the parameters of the PWM that will affect the output, which they are the frequency and the duty cycle, although the frequency doesn't have much effect on the output compared to the duty cycle. Then we will learn how to filter them, and also we will learn how to buffer it if we have time at the end of the video. So let's get started, guys. So before we start with the coding and dive into the PWM functionality and what so on, so first let me show you how to identify the PWM pins, because again, not all the IOs from the Arduino or any microcontroller, they are supporting PWM functionalities. So here, if you can see here, some of the pins, okay, some of the IOs here got this sign of wave. I'm not sure what they call, but something like this, okay? So this wave indicating that this pin is PWM or support PWM functionality. So we can see here we have Arduino Uno got pin number 3, 5, 9, 10, 11 got this sign. On the other hand, some of the Arduinos, they might directly print in the silk screen that there is a PWM signal. If you see here, let me change the color to red. If you see here, okay, we have PWM being printed in on the silk screen of the board, indicating that all these pin out, which is 2, 3, 4, 5, 7, 8, and 12, 13, they are supporting PWM functionality. So with this, we can indicate or which pins they are supporting PWM, so we can use it to output our PWM. So after we finish with the IOs, after we know which pins that support the hardware PWM, because sometimes we can bit bang the hardware. Let's say if all the PWM pin outs that we've been used already and we need more, we can use a bit bang or we software emulate the hardware, but this is not the topic of this tutorial. So after we declare and we know which pins we are going to use as a PWM, so again, you'll surprise how easy it is to output the PWM output to the pin, which can be done only in one line. Today we will use analog writes. Yep, analog writes. So analog writes takes two parameters. The first parameter is the pin, which pin you are using. For example, here. And by the way, we are focusing on Arduino Uno, this tutorial, which is exactly same if you want to go with any other Arduinos. Yeah, it's just that the frequency of the PWM might be changed, although for Arduino Uno itself, The frequency is not fixed for all the PWM channels. This is what we will see after this. However, if we want to change the frequency, we still can do, but it doesn't have much impact on the output. Anyway, so here we can choose the pin. Let's say on pin number 3 or 5 or whatever. And the value here, the value is representing or referring to the duty cycle. Okay, the duty cycle of the PWM. Let's say PWM duty cycle, and the duty cycle here is in the range of 0 all the way to 255. Okay, is for sure the 0, the output will be 0, 255, the output will be the maximum. Okay, so now I can set it any number in between. Let's say I want to set it to 100, for example, and that's it. That's it. So now we have PWM signal with 100 duty cycle. Yeah, would be output on pin number 3. So let's output on the Arduino Uno, pin 11, and then we will go to the oscilloscope and see how the signal looks like. Okay, so we can see here I already connect the oscilloscope to pin number 3, to the PWM pin number 3, and as we can see here, the PWM output. So let me zoom a bit. Hope we can focus. Okay, so you can see here the duty cycle is about 39%. Okay, so 39% of the waveform or of the output is positive, and the rest about like 61% is negative, or not negative, sorry, 0. Okay, and here we have the frequency, which is 490 Hertz. This is for channel number 3. Now I will change to channel number 5. There we go. So now I will move it to channel number 5. There we go. So this is channel number 5. So you see channel number 5, duty cycle is still the same, about 39%. However, the frequency is 976.5 Hertz. The frequency here is higher on channel number 5. Now I'll move to channel number 6. And by the way, this is the same parameter or the value I sent to the PWM function. I just changing the channel. So now I move to number 6. There we go. So you can see here 6 also same. It has a 39% duty cycle with 976.5 frequency. Now I will move it to channel number 9. Here it is. So this is channel number 9. So we notice the channel number 9 again, duty cycle is the same, but the frequency dropped to 490 Hertz again. Now I'll test channel number 10. Here it is. So this is the readings for channel number 10. 39% duty cycle with 490 Hertz. Now I will move to last channel, number 11. Here it is. And again, number 11 duty cycle is 39 and the frequency is 490 Hertz. From here we can see that two channels are providing higher frequency compared to the rest, which is 970 Hertz, 0.5 at channel number 5 and 6. And the rest of the channels, which they are 3, 10, 9 and 11, they are producing 470 or 490 Hertz with the same duty cycle for all the channels. So again, I will work on channel number 3. Let's go. Okay, so now I reactivate channel 3, as you can see here, 39% duty cycle and 490 Hertz. So in order to change the duty cycle of this channel is as easy as changing this value, the one we talked about just now, which is ranging from 0 to 255. So if I set 0 here and I upload again, let's see the output behavior. There we go. We see the output is just a 0 here. And if I set it all the way to 255, there it is. So if I set to 255, so we can see is a pure 5 volts. I set here the channel 1 is a 2 volts, so we have 2, 4 and half, so about 5 volts. So in between, definitely there will be the different duty cycle. Let's say if I change to 10% or 10, actually, sorry, this 10 is not the percent, but just a number that's representing some duty cycle, as we will see. It is. So now if I set it to 10, so the duty cycle is 3.9%. Now I'll increase more, let's say 150. There we go. The duty cycle is 58.5 and the frequency is fixed. All the way if I go to, let's say, 220, so the duty cycle will be increased accordingly. There we go. You see the duty cycle now is 86.2%. And so on and so forth. So by altering this value here, we will have a different duty cycle of our PWM output. So now, guys, if we want to change the frequency of the PWM, which we are referring to the hardware PWM pins, so here I have made some cheat sheet for you guys to follow. So we start from here. These are the pins I have divided into 3 groups following the timers. So every 2 pins, they are linked to a timer. So here we have D3, D11, which are the outputting maximum of 490 Hertz, 490.2. They are linked to timer number 2. D5, D6, where they are outputting maximum of 976.5 Hertz. They are linked to timer 0. And D9, D10, where they are outputting 490 Hertz, they are linked to timer number 2. So if we want to change the frequency, we just need to change the registers. Now we need to touch the registers of these timers to change the output frequencies. So which timer we need, or exactly which register that we want to touch is this TCCRNB, which is the timer counter control register. Okay, N here representing the number of the timer, whether we want to timer 1, timer 2, or timer 0. So for example, if we want to set timer 2, which is mean we are playing with D3 or D11, so we need to set the TCCR2B. Okay, so this is exactly what we will see in the following. And in this counter, in this register that belong to this timer, timer 2, we have about 7 bits, as we will see later in the data sheet. So we need to focus on these 3 bits, which is CS, or the counter select, clock select 20, clock select 21, clock select 22. So if we open the data sheet, so here I download the data sheet of the Atmega 328P. This is the one that came with Arduino Uno, and we go to section I guess 17. Let me see. Yeah, 17 point. Wait. So 17, 14, 15. 17. Okay, so this section 17 talks about the timers and counters that are linked to the PWM. Then we go to 1711. Yes, registers. From the registers, we want to go to, let me increase this, not TCCRA, we want to go to the B. Yeah, exactly this one. So if you can see here, guys, we have, nope, this is, sorry, so yeah, this is CRB, so go to select more. Yeah, so let me take a screenshot of this so we can comment on it. So if you see here, this is the register that we are talking about, the TCCRB. This is the one that we will modify to change the frequency. And these are the 3 bits that set the frequency, as we will see later. So by changing the bits here, okay, whether we are setting to 1s or 0s, the frequency will be, the output frequency will be changed. But again, we need to follow the presets dividers, because again, these 3 bits, okay, they are the one that's responsible to select, or what they call the divider of the clock cycle. So again, when we change the dividers of the clock cycle, in return we'll change the output frequency. So we can see here, if we set them all to 0s, okay, these 3 bits, the first 3 bits are from the right. If we set them all to 0s, we can see here no clock source. Is mean the counter or the timer will be off or shut down. Or here mentioned the datasheet is stopped. So if we set the CS20 to 1, here we will get the maximum output frequency because we have no divider. We won't divide it to anything. So the whole of clock cycles will be output as a frequency. So we have no prescaling. And if we set only CS or count, what they call clock select 21, so it will be divided by 8. If we set these 2, which is CS 2021, we divide by 32, and all the way, if we set 3 of them, we divide by 1024, which is the very, very slowest frequency. So again, we go back to our cheat sheet here. So again, these 3 bits that we are going to play with to change the frequency, okay, as we saw in the data sheet. So now after we know the roles of these registers and the bits, so now we need to continue with the cheat sheet to see how to set the frequencies. So now I will talk about the D3 and D11. And again, as we said, we need to set the TCCR to B, okay? And we just need to change the first 3 bits from the right, okay? So if we set it, this is the command, by the way, that we can just copy paste to the Arduino IDE, and it will change the frequency for us. So if we set the only one, which is, I believe, the CS20, we get the maximum frequency of about 31 kilohertz. If we set the second one and reset the first one, we will get about 3.9K, and etc. the rest of the frequencies. And regarding the D5, D6, we have only this range of settings, where the first one will give us maximum of 26.5 kilohertz, and if we set only the second one, will give us 7.8 kilohertz, and all the way to the 61 hertz. And the last one, D9 to D10, that they are related to timer 1. So this is their settings, where the first or the maximum output frequency could be the 31.3 kilohertz, and the minimum will be 30 hertz. And however, the default, guys, if you see, I already mentioned for you guys, the default here is the third bit being set, which is CS22. The third bit, when we set the third bit, so the output will be only 490 hertz, and the second group will be 976, and the D9, D10 will be 490 hertz. And again, we have to notice the frequencies are fixed. It means only these output we can get. We can get more or less, or even we can get in between. Okay, so these are the fixed steps that we can change them. So for example, the first step of this group will be 31.3 kilohertz. The second step will be 3.9 kilohertz. In between, we can get it for the time being. Okay, guys, so this is what it is for changing the frequency. So now we can go to the IDE and try to set some frequency and measure it with the oscilloscope. Okay, so now guys, let me bring this down. So let's try to set the frequency. So here I send analog signal or PWM signal to pin number 3 with 127 value, which is about 50% duty cycle. So now let me go to the cheat sheet again. So we are here now. Okay, we're setting the default of 490, as you can see here. Let me zoom in the oscilloscope. Let me see. Let's focus. So as you can see here, the frequency is 490, which is the default. So now let's say if I want to increase the frequency, I just need to copy this guy and paste it here. So we can say to change the PWM frequency. Okay, so now when I set only the first bit, so I expect the frequency to go up to 31 kilohertz. So let's compile and send to the Arduino and see the output. Here we go. So let me open, repeat the time so you can see the waveform, and yep, here we go. You can see the frequency is 32.2 K. Okay, so the frequency been updated to the max. Now let me see if we can change more, for example, to this, which is about 980 hertz. Okay, go. Let me increase the time. Here we go. So we have 980 hertz. Good. And so on and so forth with the rest of the settings that go to the 30. So this one should give us 30 hertz. Okay, almost done. Reduce the time. And here we go, 30.6 hertz. So with this guy, we have learned how to output the PWM signals, and also we have learned how to change the duty cycle and the frequency. Well, guys, so after we have learned how to generate the PWM and also how to change the parameters of the PWM, which is the duty cycle and the frequency. So now is a time where we will learn how to filter out the PWM signal and generate the DC out of it. So here we need to use a low pass filter for sure, which is looks like this. So this is the output of the PWM. This is how it looks like. Then we need to construct this simple circuit, which it's called low pass filter, LPF for short. So if we draw the, let me take a snapshot of this. If we draw the PWM signal in frequency domain, we will get something like this. Okay, we'll go here, then it will drop. where at this point where the frequency drop, this is the frequency of the PWM. So this is the PWM. Sorry guys, is not clear, I know. I promise to improve it in the future, but anyway, it is the PWM frequency. Okay, enter here, which is in this time I will choose the higher frequency available in all the pin out, which is about 62 if I'm not mistaken. Yeah, it's 62 kilohertz. Okay, because I'm planning to use this later in the future tutorials. I will use this for this DC-DC converter control system. So I just take the highest frequency, which is give me higher stability in the output. However, still not that concern if you want to choose lower frequency. I already tried that and it's proved that it works. Anyway, so yeah, since I'm working on 62K, so this is the cut or the maximum frequency that PWM can be generated with 62 kilohertz. However, if I want to design my circuit, I want to design my low pass filter, for sure you need something called cutoff frequency, which is it should be about 10 to 20% lower. Okay, this is the cut frequency should be lower than the PWM frequency by 10 to 20%. Okay, if you see here, I put for you guys a note here that the cutoff frequency of the low pass filter that we are going to design, it should be 10 to 20% less than the PWM, which is 62K, so less than by 10, 20, about 6K. So the cutoff frequency of my LPF or low pass filter, it should be 6K only. Why we need that? Because later we will need it in the calculation. So now if I want to, and by the way, before we go to the calculation, this kind of filter or this star filter is a low pass filter, but this construction at only we use R and C, only one R, one C is considered as a first order low pass filter. Second order, we just need to duplicate it. Okay, so this is the equation where we put the cutoff frequency 2 pi and 1 on the tops to calculate the RC, which is the resistance and capacitance. Okay, so we substitute all the parameters here, all the variables to calculate the R and C. So here I already calculate for you guys. So again, we can have a different options. These are can follow the components that are available with you, or you can just order online if you don't have any stock. So for me, I calculate 3 levels or 3 systems that I can choose either one. So first one is 26.5 kilo ohm. However, if I want to use the standard value, it must be 27K, which is not much different, and 1 nanofarad capacitor. The second system is 982 ohm, which is about 1K, and 27 nanofarad. The third one is 3.9K, which is standard already, and 6.8 nanofarad. Okay. So with these 3 systems, I can choose either one. I guess I will go with the second one. Okay, which is 1K and 27 nanofarad because I have the components with me. Then I will try to construct the circuit, then we test it on the oscilloscope. However, as we will see later, the output might not be that, how can I say, not that smooth. We still can see some ripple. So due to that ripple in the output, I might suggest to go with the second order low pass filter, which is second order low pass filter. Again, we just need to duplicate it. If I make a new copy of this or a screenshot. So this is again the first order. If I want to go second order, at the output I will add more resistor here and capacitor to the ground. So this will be my output here. Okay, so yeah, now with this I will have the second order LPF. Okay guys, so yeah, as we will see later, we will construct the first order first, then we see what's the issue, then we add the second order, then we will see whether it will fix it or no. So yeah, this is the calculation, and again remember the cutoff frequency of the low pass filters must be about 10 to 20% less than the PWM frequency. Remember, that is very important to give you a stable DC voltage. Okay guys, so here is our filtering circuit. So if you can see here, this is the first order filter. This is the resistor and the capacitor, and this is the second order filter, which is these three resistors, which I don't have one complete resistor, but I substitute with these three resistors and this one capacitor. Okay, so this is the first stage, this is the second stage. So now let's connect to the oscilloscope and see the readings. So now I will try to measure the input, which is the PWM. You can see here, this is my input. Okay, you can see here, this is the input, which is 62 kilohertz, duty cycle 47. So now I'll measure the first stage of the low pass filter. If you notice, it's been filtered out already. However, it's not pure DC. You can see the ripple of the output is about like 60%, more than 60% of volt, which is about 50 millivolt or so. So that's why I add the second stage. If you see here, the output of the second stage is much more nicer. Okay, so again, here is the pure PWM input. Here is the first stage where we still can see the ripple, not very clear. So when I added the second stage, you can see the output is much cleaner now. So with this, I can see that this DC voltage is ready to be buffered and used for the other application. Okay, for at this stage, you need to make sure, guys, the output of this, although is clean and nice and filtered, however, this output is still just a signal. It still cannot be used for heavy application like power and LED, or even being injected to control a DC-DC converter. So that's why we need to buffer it using the op-amp, so it can be used for that application. Well, so now before we go and draft the buffer circuit, let's talk about the op-amp that we are going to use in that circuit. So here I will use the LM358 from Onsemi. It's a really popular amplifier, or actually it's a dual amp. If you can see the inner constructions of the IC, it's got two op amps where we can use it to to buffer two signals. If let's say we have two PWM signals, after we filter them out, so we can use this one IC to buffer two signals. And also I like to use this IC because it supports very wide range of VCC from 3 to 32 volt. And yeah, I got a lot of good features related to the ESD protections and other things. Yeah, so in this tutorial I will use the LM358, and again here is the pin out of the IC. So now we can go and draw the schematic of the buffer circuit. Okay guys, so before we talk about the buffer circuit and talk about the gain and the inverting and inverting circuit, let's discuss why we need the buffer. Okay, for example, if I have an MCU, okay, so I have MCU here that outputting a PWM signal or anything, then okay, since we're talking about the PWM, then I already filter out the what I call the signal using the low pass filter. Here is my cat, go to the ground. Okay, let's say I have only first order filter. Then here for sure will be my output, or what we call DC output. Okay, so why do we need buffer? Why don't we use this signal directly? The thing is, let's say if I use this signal, for example, to connect to my load, okay, because at the end of the day I have some load, okay, whether it's LED or DC-DC converter or whatever. So if I directly connect my signal to my load, and this signal definitely will have a ground. So if you see that the load will draw the current from where? From the MCU. Okay, so the MCU will consider the current supply to the load. Okay, if you see here is direct connection to the load, and we know most of the MCU can support very low magnitude of amps, which is about in terms of micro to milliamps only. And sometimes our load might require very high amps. Okay, so this one high amp. So how to solve this issue? Okay, how to solve that we can support very high load and without damaging our MCU? Then we can introduce the buffer. So if we add the buffer here, okay, this one later we will learn how to design our buffer. Okay, so if we add our buffer here, later we will talk in details about our buffer, but here just I will draw for you, for example. Again, I will draw the non-inverting with gain equal to 1. So on here will be connected to our PWM. And now, for sure, as we know, the buffer or the op-amp, okay, so this one again is just an op-amp, so they have its own VCC and ground. So when the signal comes to here, then into the op-amp, we know that the impedance of the op-amp, okay, the impedance here is very high, almost equal to infinity. Very, very high impedance here. So it means there will be no current go to the op-amp. So we will protect our MCU from being overloaded. Then how we will get the output here then? It will be from our VCC or from the VCC of the op-amp. So the VCC of the op-amp will be connected to the output following the magnitude of the input. Okay, so now if I connect this guy to the load again, I will be not scared of drawing very high current from my MCU. Okay, so the MCU will be happily protected. So that's why we guys need to use the buffer circuit to mostly isolate and protect our MCU from high load. Okay, so now we can go and discuss further about the buffer circuits and how we can implement it. Okay guys, so now if we talk about the buffer circuit, so since we are using a buffer or since we are designing a buffer circuit, so definitely the what we call the gain, so the gain it should be equal to 1 only. Okay, so we have no what they call no gain, so it means that the output will be equal to the input. Okay, so we don't have any increment or decrement in the level of voltage between these two. Otherwise, it depends on the application. If we want to add some gain to it, for example, my input circuit, or which input will be the PWM signal, is very low compared to the output signal. The PWM signal usually is 3.3 volts or 5 volts, okay? But my output, let's say, but my output signal, I want it to be, for example, let's say 30 volts, Okay, so since 30 volts, so is mean I need to have gain of 10 times. So then if I designing the buffer, I need to add 10 times the gain. But for now, I'm okay. I mean, the 5 volts should be okay for me for the time being, because it's just for example. I don't have a specific application to decide what is my output. Okay, so far I will continue that the output is equal to the input, so it means my gain will be equal to 1. So since my gain will be equal to 1, so the circuit, okay, so let's draw an op-amp here. So this is the positive input, this is the negative input, this is the output. So I have one here, one here. So yeah, to design the non-inverting what they call buffer with the gain equal to 1, so the negative input will be connected to the output. Okay, so this will be my out, and the input will be here. Okay, so this is the non-inverting buffer. Okay. So now let me screenshot the pinout of our LM op-amp, then we see how to design the circuit based on that one. There we go. So this is our op-amp. You see we have two halves. So first I will connect the pin number 8 to VCC. So this one will go to VCC. Okay, and ground go to ground. Okay. Then since if we see here again in the circuit we draw just now, so the negative input will be connected all the way to the output. Okay, so here I will take only the first half of the op-amp. So I will connect the negative with the output or pin number 1. Then I'll take one wire of here that's representing the output. Then the input will be connected to pin number 3. Okay, this is my input. Okay, so yeah, I guess that's it. So now we can go and implement the circuit. Okay, guys, so here I already connected our LM op-amps, the breadboards, and you can see here, I'm sorry if it's not clear. So now the op-amp is upside down, so the notch is here, so it means this is pin number 1, so all the electrons will fall down. So for sure this is pin number 1 because the notch is here, so this is pin number 1 is being connected and shorted to pin number 2, and this is our output. You see connected to the oscilloscope. Pin number 2 connected to the 1, as we said. Pin number 3 is the input. I took it from here. This is our first order, second order, this low pass filter. This is the output connected to pin number 3. And what else? Pin number 4 is the ground, I believe, if I'm not mistaken. And pin number 8 is our VCC connected to the 5 volt. But for sure, this one is not, it shouldn't be connected to the same source as the Arduino, because again the Arduino will not supply that much of current. It should be an external or directly connected to the power supply of the circuit. But this one, just for the sake of demonstration, I connected to the VCC of the Arduino. So now we can go and see the output at the oscilloscope. There we go. So you can see here, this is the output connected to pin number 1, and you see how nice and stable the output is. Now let's check all the stages from the PWM all the way to the op-amp. So let me release the lead for the oscilloscope. So now you can see I will hook the op-amp, the pure op-amp without filtering, which should be this guy. You see, guys, this is the pure op-amp without any filtering. Now I will go to the first order filter, low pass filter. Here we go. Now I'll go to the second order You see how nice and clean now, better. Now I'll connect it to the buffer, which is this pin here, pin number 1. Here we go. You see, notice that pin, what they call the output from the buffer and the output from the second stage of the low pass filter is not much different, almost the same, which is correct because our buffer has a gain of 1. Okay, so there is no different for output compared to the inputs. So now, guys, we have learned a lot in this tutorial, I believe. We learned how to generate the PWM, how to control the duty cycle, how to control the frequency. Then we learn how to filter them out, how to add the first order and the second order low pass filter, and also we discuss about the buffer circuits. So now just a bonus for you guys, don't go yet. I will give you a small code update where we will use the potentiometer to control the level of the voltage, because if you see now, the level of the voltage is static. Okay, the voltage is static because our code is just send only one level of voltage. So now we will find the potentiometer connected to our ADC, then the ADC will process the signal and send it back to the PWM, so we can control the level or the magnitude of the V out from the PWM. Okay guys, so now we will start to develop the code for the potentiometer, the bonus code that we will use the potentiometer to control the V out. The DC V out, or control actually the PWM when after we filter out will be our V out. So now we will add on, we will use the same code before that we used it previously, and we will add our new potentiometer so we can control this number, okay, which is the duty cycle. What we can do is okay, so I want to, now I'm connecting the potentiometer to a 0 to analog channel 0. Later I'll show you when I open the camera for the hardware setup. So now I will declare my, what they call, define, let's say, analog inputs as a 0, okay. What else I want to do is in the loop. So in the loop, what I want, first I need to read it. So I will say integer analog value equal to analog read Okay, analog read from the analog in. Analog in, yep. Okay, so I will read the analog value, okay, from the analog input, which is the A0. Then I read it here. This one, the what they call the range or the magnitude of the value will be from 0 to 1023. So we need to map it, or we need to just divide by 4 or just map. I mean, either way should be correct. So I will be define integer, let's say final underscore value equal to map of what I want to map. I want to map the analog value. Yep. Analog value again is from 0 to 1023. I want to map it to 0 to 55. Okay, because the value here, or the duty cycle, it should be from 0 to 55. Okay, so here I'm mapping it. I map the analog value from 0 to 1023 to 0 to 55. Okay. What else? I guess that's it. That's it, guys. So now I take the final value and send it to here. So now let's try to upload and we see if everything correct. Got an error. Analogged should be read. Yep. Okay, good, done already. So now let's go and test our circuit and see if we can control the V out using the potentiometer. Okay, so as you can see here, this is the potentiometer I added just now. I connected one pin to the VCC and the one to the ground, and the middle one or the white part connected to the ADC channel. Okay, so now I'll try to, it's not easy to do it on the camera, but I'll try to rotate the potentiometer and you see the voltage is increasing. Here we go. Voltage is increasing all the way to about 5 volt. Then I rotate the other way, then should go down. Yep. So yeah, you can see now. And sorry guys, you can see that a lot of noise here because of the connection or the loosey connection of the potentiometer. So that's normal because we have not soldered it perfectly, just plug it using the breadboard. So again, now you can go up and go down using the potentiometer, okay? So now we don't need to hard code the value of the PWM rather than just connect that potentiometer and adjust the duty cycle. Okay guys, so I believe that's it for this tutorial. It's kind of lengthy tutorial already, so just to recap what we were discussing on this tutorial, we talked about the PWM signal, how to change the duty cycle frequency, and also we talked about the low pass filter, single and double stage, and also buffering the value. Then we saw how to filter out and how nice it is and how it's near to a DC VOut that we can use it for many applications like injected to DC-DC converter to control the VOut, or even can use it to dim an LED or any other applications. So with that, we have reached to the end of the tutorial. Happy learning and see you soon.